Yes, hello, my name is Elmer, alias Short, and I would like to introduce you to my bert on an FPGA project. So, first of all, I would like to show a little bit about how bert works. Then I would like to give you a short demo about the implementation that I did. So first of all, bert is an arcade game from the 80s, and it has been produced by Gottlieb. The hardware has been built also by Gottlieb and then later by Milestar. And the hardware is actually capable of running a couple of different arcade games. But I would like to focus on bert for the time being, and I will also show you then what kind of games I have been implemented in addition to it. So luckily those arcade games came with an operational manual, and this manual is containing also the schematics. This is basically enough to redo the whole game and reproduce the whole game in an FPGA, as it shows what components are used, and it also shows how they are wired up. So before starting the demonstration, I would like to just very quickly go into the hardware and show you how it works. So the Gottlieb system contains of two different cards. The first one, which is called the logic board assembly. And this logic board assembly contains an 8088 CPU here. That's the main CPU which is executing the game code. As you can see, it comes with a watchdog timer, and it also comes with a clock driver here. The CPU is working with program memory. It's basically 5 EPROMs. In total it's 5 times 8 kilobytes. And there the game code is stored. We also have, as any CPU needs, some RAM. We have 6 sockets of 2 kilobyte of RAM. You can also see there is 2 sockets, ROM A and ROM B, which can be used for extending the program ROM by plugging in ROMs instead of RAMs. So if you don't need all the RAMs, or if you would like to extend the program ROM, you can use those sockets and plug in 4K each in here. Which is actually used by Krull. We also find that there is I/O sections here. So this is the input section. You can see here that there is different buffer drivers here. The dip switches, which are selecting the game configuration, is sitting on one of those. They're selected by the CPU with the address bus here. You also see there is a socket where you can plug in a trackball, for example for a Reactor, or a rotary controller for map planets. And then there is 16 lines which are connected to just the standard inputs like buttons, joysticks, coin switches, and so on and so forth. On the other hand, we have the output section, and there you can see that we have a coin meter. We have the knocker, the pinball knocker, which is famous in bert. We have some signals which are defining the priority of foreground and background sprites on the screen. We have some signals which are controlling the flipping and the flopping of the screen, which is used once you configure the game in cocktail mode. So the screen moves upside down for the second player. There is also 16 lines which are used for putting data out. But this bus here partly is used for the sound bus, so you can send out sound codes that the sound assembly should play, which is the second board in that design. If we move over, then we see that we have on the second sheet of the schematics the video system, which is basically the graphic cards of your card game. We see here that it has its own crystal at 20 MHz with 2 D flip-flops going down to a horizontal clock of 5 MHz. Which is then defining the CGA, 15 kHz line rate. We have 2 daisy chain counters here, which are counting up the horizontal position from 0 to 255. We also have the vertical counter here, which is counting up from 0 to 239 for the visible picture, and then it's also a little bit more for vertical blanking. We find that we have some logic here which is doing the horizontal flipping, and we have also here vertical flopping, this portion here. Then for the foreground portion of the design, we actually find 3 large RAMs here. The foreground vertical position register, the foreground horizontal position register, and the foreground object select register. And how it works is that the CPU is writing in object data into the 3 registers for the objects, the foreground objects, to be displayed on the next frame. And it's actually writing for each object the vertical position, the horizontal position, and the actual object number. So which object should be displayed for the next frames. They have 64 rows in here, so you can display 64 objects. Now what is happening is that the picture, the frame, is built up line by line. So what you have is a vertical position detector which actually checks if an object is placed on a given scan line, the actual scan line that we're in. And once it figures out that an object is contributing, or some objects are contributing to the next scan line with a row of pixels, it will detect that, and it will actually copy the horizontal position data, so the x coordinate, into those RAMs here. So it's basically filtering all the objects here into RAMs here, which are then just accounting for the next scan line. Also, we have here the object number for that specific object that should be displayed on the next line. Also, the detector is figuring out where the actual scan line, so the y coordinate, is cutting through the object. And this number is basically the relative number within the sprite, the foreground sprite, that's copied over in those 2 RAMs here. So in total, each of them is 16, so in total that's 32 objects that can contribute to the next scan line. Now if you keep going, we actually figure out that there is 2 line buffers in that design here for the foreground. And it works in such a way that these line buffers are, one is read and one is written. And the one that is written is actually written with the line data for the next line coming up. And this one is previously written with the line before. So they are always flipping between each other, where one is read and one is written. So how is now the line buffer that is actually getting written filled up with the pixel data of the objects that are detected by the vertical position detector? It works in such a way that there is actually foreground object ROMs, 4 × 8K. And those ROMs are containing the pixel data, so basically the color of the foreground objects. And the registers, addresses that you have here, are a combination of the object number, so you know which object you would like to look into, and also of the absolute position, the line within the object, which is generated from those RAMs before that we talked about. And the horizontal position is the position where you would like to fill up the line RAM. So those LBA lines are basically, once you write them, the horizontal positions, and the data that comes in is the right portion of the sprite from the foreground ROMs, from those ROMs here. The information that is going into the line buffer is read out in parallel here with 8 bits from those foreground object ROMs, and they need to be serialized, and that's what those 4 shift registers are doing. So each ROM that you have here is basically containing 4 pixel data in each of the rows here. And then in the end you get the foreground video signal, which is the 4-bit pixel data that you get out here. So that's about how the foreground logic is working. The background logic is a little simpler. This starts here. What you have there is a background character register, and that background character register is holding the different characters, so the background character objects, the numbers that you would like to display in the frame. So the background is, unlike the foreground, built on a tile grid, where you have tiles which are regularly cutting the screen into pieces, basically. And as there are approximately 1,000 character or tile positions on the screen, this is a 1K RAM here, where each row is mapping to one specific tile position on the screen, and the number that is in that row written in that memory defines which character should be written on that screen. So that's the object number here. So what is happening is that this one can be written and can be read by the CPU. In order for that to work out most of the time, the data in here in the first half of the vertical blanking window is copied over to the background buffer RAM here. So once this is copied over, we are a DMA transfer. So this is done automatically by using those horizontal and vertical counters. This one can be used as a regular RAM by the CPU, and the CPU has to be stalled, so it's not allowed to actually write into that one during the DMA transfer. So there is a ready signal on the CPU which is pulled low. So the CPU is inserting wait states. It's wait cycles basically until the RAM is again good to write or read from. Once we have those characters copied over to the background buffer RAM, they're generating the different information for the background character RAMs here. So those RAMs are containing the object data, so really the pixel data, the colors. And those address lines here are then given by the vertical and the horizontal positions that we are in. So it's which tile we are in. And the data coming out here is then the pixel data, which is just mapped back here towards the background video on that side here. An interesting thing to note about this is that you can either plug in ROMs here, so just burn the data into the ROMs and plug it into those sockets, or it can also be equipped with RAMs here, which means that the CPU can also write those RAMs to define different characters here, objects, background objects, which basically extends it over the memory that you have in a ROM here, because you can change those frame by frame. And a couple of games are actually using this, like for example Krull. If we go back here where we have the foreground and the background video signals coming in, then we figure out that there is a foreground background priority logic here. And I've seen before the CPU is actually steering that FP priority signal here. What it can do, it can swap background and foreground, which is the case if cuboid, for example, hops behind the pyramid. Then this one is triggered here. That signal here then is multiplexed out either from forward or backward, depending on the FP priority signal, and goes into color RAMs. And there are 3 color RAMs in here. And those color RAMs are defining how those pixel laders are mapped to different voltage settings. So this is just a resistor ladder here on all these outputs, which is basically digital analog converting to an analog voltage level here. By putting in different settings or different parameters in those RAMs, you can set up different palettes, color palettes. And this selects a couple of colors from the 4,000 colors that are possible. You can also see there is color write signals, so the CPU can change those. So different games have different palettes. It would be even possible to change the palette within the game. And that's also used as well. And you see now here there is the red, green and blue signal which goes to the CRT screen together with the horizontal and vertical sync in the video grant. So that all together is the logic assembly. And what I did on the FPGA is that I took all those different chips here, and you can see, for example, 11 here is a 221 MUX, a 74157. So you can get the data sheets and you can figure out how that this portion is working here. And you can then make a replica in code, in VHDL in my case, for that specific portion. If you start doing then, you can actually replace or you can reproduce all of that schematics in the FPGA by Verilog or VHDL code. And then you wire it up and then you have the original hardware once it synthesizes on the FPGA. So that's what I have been doing, including also the 8088 CPU. If we go forward, we also see that there is a sound speech assembly. That's how it looks like. Excuse me, and that's the second card that you find in the card game system. So how does that work? We first of all figure out there is an own CPU for that one. It's a Rockwell 6502 CPU. And this CPU is also clocked by known crystal here on that side. It's basically roughly 1 megahertz clock that is going in there. We see that this CPU also has its program ROMs. It has 2 banks, the U5 and the U6. And there is a lot of different jumper settings here, so you can either make it 2K, 2K, 4K, 4K. And in the second later generation, it's even also 3 times 8K that you can plug in here. So this is where the program code is basically the code is basically sitting for the Rockwell to work. On the other hand, we have a Riot 6532 chip. This one is riot stands for I/O timing. So what this has, it has 2 banks of 8-bit inputs and outputs, and they're just used as inputs. And you see here that on that PA inputs, the sound bus from the video assembly is coming in, together with a strobe signal, which is indicating that there is a new sound to be played by that board. So what is happening, if there is a non-zero pattern coming here, there is a strobe getting in, this riot will actually raise an RIQ, so an interrupt towards the CPU, and the CPU will fetch that from the riot, this digital pattern here, and then we'll start playing that sound. We also see that there is a PB, so the second input, which is used with dip switches and the test switch for testing the card basically. So here you can put in which kind of sound code you want to play, and then you put the switch, and then it plays it. Also the riot has RAM, that's the R in the riot, so it has 128 bytes of RAM that the CPU is just using as regular CPU RAM. If we go forward, we figure out there is also 2 digital to analog converters. If we focus on that one first, the U20, and this is connected directly to the data bus and selected by a given address space or address information here from the CPU. So the CPU can just put a digital data here, which is then converted to an analog signal, which is then directly mixed with other signals on the audio out. So the audio output, which is then amplified and goes to the speaker. We also see that the second AD converter is driving the voice synthesizer here on the master clock. So the CPU can set up different voice clocks on the SC01, which is, as I said, the voice synthesizer. Also the CPU can change the pitch of the signal with this I1, I2, and the phonemes are coming in directly from the data bus here. So it's 64s that you can actually play out here. Also you see there is an acknowledged ready signal which is going back to the riot, and then from the riot back over the RIQ line to the CPU. What is happening is that the timing of playing out phonemes is steered by the SC01 itself. So once it's done with it, it gives a ready signal back, and then the CPU, as it gets an unmaskable interrupt, knows that it's done, it can do something else. Also, all that logic has been implemented in the FPGA. So the 6502 is a soft core in the FPGA. The Riot 6532 is a soft core in the FPGA. Those AD converters are externally. And the SC01 here has been replaced with just replaying phone names that were sampled from the original hardware. That's not really very good. It doesn't sound original, but that's the best you can do currently. So, having said that, let's take a look at the FPGA itself and how it's implemented. So that's the FPGA board. And what you see in the middle here is a Spartan 3E FPGA. It's actually that version. It has 1.6 million gates, and there is also an OR flash, 60 megabits, so 2 megabytes. This flash is storing all the program ROMs, the bootloader and the bitstream for the FPGA. So once you power it up, the bitstream is copied from the Intel Strata flash up to the FPGA, configures the hardware in the FPGA, and also the bitstream contains the bootloader, so the ROMs for the bootloader, so it comes up. Once I select the game, then it goes out to the NOR flash again, fetches all the ROMs for that specific game, copies them over into the block RAMs in here, so there is ROM cores or RAM cores sitting in there that can be used. And it also uses the NOR flash as just the program memory, so those ROMs that we saw before, just pointing to different portions within the NOR flash for the different games. So the CPU, the 8088, is fetching its instructions from the flash here, which is then offloading this 40K that we had in the ROM section. We see up here that there's this digital to analog converter. It's a 2-channel device, where one channel is used for the sound, which I have connected out to the speakers here, and the second is used for the voice. I haven't connected the voice yet here. I would have to swap that, and I will show this maybe in a later session here. So that's about it. So what you really need to get this working is a 50 megahertz crystal, which is clocking the FPGA. All the other clocks are derived in the FPGA. A flash for the ROMs for the bootloader, those are working as CPU ROM, the AD converters, and a little bit of power stuff here, so that one gets all the voltages it needs. Up here you see the VGA connector, which goes just to a regular computer monitor, computer screen. This board only gives out 1 bit per color. It's a restriction of the boards, so the colors don't look very good. But I've tested with an Nexus 2 port, which is a smaller one, which has 11 bits, and it just works fine, so that's not an issue. Getting the all the data that you have here, the proms, bit loader, bit stream, into this one is done by this serial cable, which you have to do once. So with a serial cable you can actually upload all the data through the FPGA, which is then running a small pick-up-place CPU and some code into the flash. That's the way to get it in. Once it's in the flash, it's sitting there. Even if you get the power, take the power down, it's still there. So let's take a look at it and let's play through a couple of games and see how it does. Maybe before I go there is also a couple of switches. You see 4 switches here, a couple of LEDs where you can see knockers and those kind of things, coin meter, knocker. I have cursor buttons here, and I have a rotary switch. All those different arcade games, they're using a lot of different IOs like joysticks, trackballs, rotary controllers, fire buttons. I'm very limited with those IOs here, so partly I have overmapped them or I don't have the functionality. I would need to use those connectors to take them out, and I actually did one trackball assembly for Reactor. But I will show you what I can do with it. So I just switch it on. And that's the bootloader, so you saw that it actually took it in from the flash and started up. So you can see that I have 9 games to run: Qbert, Faster, Harder, More Challenging Qbert, Insector, Krull, Curveball, Reactor, My Planets, Knightmare and Tylz. And I have set the dip switches so that we are running the games that can go in cocktail mode. So let me just check if I have the sound also up. Yes, should be good. So now I can just go up and down with my buttons here and select the game. Let's just take the most popular one, at least in my view, Qbert. So there it is. You also hear the sound in the background. Now you will only hear the sound that is generated by the first DAC. The voice portion is not coupled in right now. I will put up another video showing that one. So let's put in some under. I have this on the rotary switch. Money comes in, and I just start with a 2-player. So that's player 1. Let me just hop around a little bit here on those. That's not really very handy to play with those. Let's see if I can make it to the disc. Yes. And I just hop off. So now it goes into cocktail. So for the second player, that's now upside down as expected. Now it's even harder. Oh, that didn't work out very well. Also, you see that I have those buttons very close to the rotary switch, so if you're plucking around them, I touch them very quickly here. Okay, let's just kill the guy a couple of times. That's now player 2 again. Player 1, okay, now I have the high score stuff. I'll just put in something here, HH. What is it, O? Player 2 has another life to go. Okay, there I am, not too bad. Okay, so I've seen I've added a lot of credits because I'm always slipping over that one. I'm pressing the reset button, I'm coming back to the loader. I'm just now very quickly browsing through. Faster, harder, more challenging. Same story, can put in some money and run it. It's also running cocktail mode. Excuse me. So again, the same thing, you can hop around here. Okay, let's just go back. Now let's take a look at, for example, Krull. So there it is. I will just let it run for a couple of seconds. Ice cores are there. I'm not a daily hero today. You see the color is quite crappy because it's only 3 bits. Let me just put some money in and play a game myself. So I'm running around, let me see if I can get it here. Oh, there is one of those. Oh, got me. Okay, you get the point. Let's get the next one. Curveball. That's how it works. You can also see here that background and foreground is aligned all the way, because this one is foreground, the frame is background. You can clearly see that the one bit of color, these guys are not really showing up, but that's not an issue, it's just a fix. Okay, seen that one. Now let's go and take a look at Mad Planets. Okay, should we wait? Now let's hop over. Okay, that's about it. Maybe I should just start. But the point is that you have seen that I have the coin on that one as well, and I'm also using this for rotating the ship, so there will be a lot of coin in sounds when I start now. But don't get distracted, so I can fly around here. I can rotate it. Oops. That was not very good. I'm not really good. I would need to connect some real joysticks here. Okay. So that's about it. Now let's see what else do we have. Now we have games which are running like this. So I'm just flipping the screen over. The plan is then, and that's what I've been prototyping already a bit, and it's not really ready yet. But I would like to have some horizontal mode for keyboard and so on. I will show that a little bit later. Let's go down to, for example, Reactor. There it is. Oh, it's flipped. I will have to flip that back. You know what? I will cheat a little. I will do like this now. Let me put some money in. Let's run it for a couple of seconds. I can also play myself a little if I want to. Okay, Reactor. Just cheating again a little here. Now let's, for example, take a look at Knightmare. A prototype game, which I tried to play a little, but it's very hard because you have to steer the knight and the horse as well. So let's just wait for the startup screen. And there it is. Okay, I started. So now I should be able to move that guy up there, throw some bombs. I also move the horse down there a little. Yes, that all works, nice. Then we have Tylz. Yes, we can also put some money in. Just play the game. See, it doesn't really look good with that color scheme. Let me just walk around a little. I can shoot also. Oh, I'm done. So there was one left, I guess. Let me see which one was left. Insector. That also seems to work again, crappy colors. Okay, I guess we had all the games now. So what is missing here now is Q*bert's cubes, which I have on another design, because there you have an expansion board which is actually using 8 times 4K of foreground ROM, and that's not really fitting in that FPGA. Yeah, by the way, I also wanted to show you the device summary for the device. So you can see its slice is 23%, so on the 1600, and block RAMs is 28. So you see it's a quite small design. So the plan is to push it into a very little Spartan 6 in the end. Keyboard is going to be added. There is also a couple of second generation games like the Three Stooks and a couple of others that will be added. And I'm also planning to support Mark III with a Laserdisc support on that one, using basically NAND flash. So I'm using that guy here. Okay, so that's about it. I think my advice would be do your own designs. It's a lot of fun. It also eats a lot of time, but it's worth it. And yeah, good luck with it. Bye.